Good morning, and thank you for joining us. I am Jim Haldeman, Business Development Manager for Instrumentation at the Lesman Instrument Company. Thank you for joining us today as we discuss installation practices as it pertains to magnetic flow meters. If you have questions, please send them to me directly in the question box on the lower right portion of your screen, or simply wait to the end of Jack's presentation, and we have allocated a few minutes for questions and answers. Today's guest speaker is Jack Roushey. Jack has worked in the process instrument industry for over 45 years. He's worked with products in level, flow, pressure, temperature, and liquid analytics. Jack currently serves as the product manager for the Citrans FM magnetic flow meters for the Siemens Process Instrumentation Group. Jack has served as chapter president of the ISA in the Philadelphia area, has been published in numerous technical journals and magazines, featured in video interviews, and has produced a variety of YouTube videos on a variety of process instrumentation and digitalization topics. So without further ado, I'm going to turn the screen over to Jack, and he may begin his presentation.
Okay. And I'm going to assume that I can be seen. Because I'm still trying to figure out the system here. So am I sharing my screen at this point, or do I need to show something? There we go. I'll get there. Give me a moment. I'm new at this. Now you should be able to see it. Let's see. How's that?
That sounds good. Looks good, Jack.
Terrific. Thank you. And by the way, thank you very much for inviting me today, and for everybody online, I appreciate your attending. So what I want to do today is acknowledge first and foremost that as a provider of flow metering equipment, as any manufacturer of flow metering equipment, it does, we basically write our specifications around the perfect installation parameters. Unfortunately, we know that in many cases, installing a meter in the perfect configuration is not possible with where your process is located, where your readings have to be taken, etc. Which is why I'm referring to this as accuracy and an imperfect world. So what I want to do today is just briefly go through what a magmeter is and how it works, just in case anybody isn't quite aware. We'll touch on that very briefly. Then I'm going to move into what are the ideal installation parameters in order to achieve maximum or optimum performance. And then we'll talk about at the end what can be done and what you could expect if you have conditions that are, in this case, less than perfect, or in some cases absolutely awful. So let's take a look at that. Let's go through these one step at a time. And as Jim said, we'll try to address your questions. If you can wait till the end, that's fine. If it's something that needs to be asked right away, make that note and Jim will interrupt me. Okay, so let's talk a little bit about what a magmeter is and how it works. This is the math. It's Faraday's law of electromagnetic induction. My response to that usually is, what the heck? There's got to be a simpler way of explaining this, and there is. So let's take a look at it. In a simple format, what basically happens is you have a conductive liquid that's passing through a magnetic field. And Faraday's law effectively says that if a conductive liquid passes through a magnetic field, it's going to create a voltage. And that voltage is going to go up as the flow rate goes up and go down as the flow rate goes down. Now, very quickly, what question I get asked regularly is, well, what happens if the electrical properties of my liquid change? And the answer to that question basically is, it does not affect the performance, the accuracy of the meter as a whole. The voltage that's induced is regardless of the conductivity of the liquid, as long as you meet the minimum conductivity, which in most cases is somewhere around 5 microsiemens per centimeter. If the conductivity goes up, all that does basically is it improves the strength of the signal, And the only real impact on it is if you've got a remotely mounted transmitter, it means that the strength of the signal between the sensor and the transmitter is going to be a little stronger, which may accommodate longer distances of travel, etc. But as far as the performance of the meter is concerned, meet the minimum conductivity, and you're going to get a meter, and that voltage that is put out is going to be directly related to the velocity going through the meter, and will not be affected by changes in conductivity. So that's the basics of how a magmeter works. Now, how does a magmeter actually make that happen? I know. Let's get over the science and let's get into the particulars. So basically, what happens is, the way a magmeter looks, and we're looking, we're looking right into the process pipe here, is the process flows through and the instrument measures the flow rate. Now, the heart and soul of the meter is there's no moving parts, and there's very little to no obstruction in almost all magmeter cases. There are some designs that have different than a concentric type design. I'm not going to get into that today, but I will say most magmeters basically react like a pipe. And what you have, the two critical pieces that are process wetted, are the liner and the electrodes. So the liner, which we're showing here, is a non-conductive material. And the reason it's a non-conductive material, as I mentioned, Faraday's law basically induces a voltage. And it's a very low voltage in most cases. And what we want to do is we want that voltage to get where it can do the most good, and we can turn it into a signal that can be used. By having an insulated, almost fully insulated pipe, you effectively reduce the path of least resistance to a very specific point, and that point happens to be the electrode, in this case, the measuring electrodes. So what happens is the voltage goes to those electrodes, and that then sends the signal up through into the transmitter, and then the transmitter converts it into something that you can use. If it's analog, it's going to convert it into a 4 to 20 milliamp signal, or maybe a pulse output. If it's a digital output, it could be Modbus, it could be Profibus, it could be Ethernet, it could be any number of different digital or analog type protocols. But what it's doing is it's converting that raw signal into something that you can do. It's also conditioning the signal based on the calibration that the meter went through, so that the flow rate that's indicated or is transmitted from the magmeter itself is linear in relation to flow, and is, in the case of an ideal installation, anywhere from a 0.2 to 0.4% accuracy. So let's talk a little bit about what a magmeter can and can't do, just to give you a quick rundown. It works, as I said already, on conductive liquids. Because it's basically an open pipe, it's relatively insensitive to viscous liquids. In many cases, because the liner actually is slipperier than the pipe, the pressure drop across the meter may actually be lower than the corresponding pipe would be. But it can handle higher viscosity liquids because there's no moving parts and no obstructions. And it's also an excellent way of measuring slurries. Where it doesn't work is it doesn't work in non-conductive liquids. So it doesn't like pure hydrocarbons. It doesn't like pure acids and bases. And that's not a major problem in most cases, because in most cases, your pure acids and bases aren't going through pipes anyway. There's normally some sort of a water base to that. And as long as that water base isn't deionized water, then there's probably going to be enough conductivity, even in high concentration liquid acids and bases, for it to work. Doesn't work with things like animal fats, that sort of thing. And it's not a gas or a steam meter. It is a liquid meter only. So that's just the basics of magmeters, just to get everybody on the same page. The second, along with making sure that your process is the right type of process, the second most critical thing is, how do you mount the meter? The first thing that you need to know is that a magmeter requires a full pipe. I showed you that picture of the electrodes earlier. As long as those electrodes are covered, the meter is going to assume a full pipe. And that means it's going to measure a velocity, and that velocity is going to be converted into a flow rate based on a full pipe. If the pipe isn't full, that velocity and the flow rate don't correspond with each other. So what we basically recommend, again, optimally, would be that the flow be in a vertical path going up, and that way you would assure a full pipe. Now, that having been said, many Magmeters are installed in horizontal locations, and I've even seen Magmeters installed in vertical locations with the flow going down. As long as the pipe is full, I really don't care. That's not important. We give recommendations to basically raise the probability of a full pipe as close to 100% as possible. The other thing you want, and this is what we're going to talk about today, is you want a good flow profile, and I'll talk about that in just a moment. What we and most manufacturers of Magmeters basically say is, as long as you have 5 diameters of pipe upstream of the meter that's straight and the same size as the meter itself, and another 3 diameters downstream of the same straight runs, same diameter type of piping, you're going to get a flow profile that will give you optimum performance. And as I said before, it varies a little from manufacturer to manufacturer and from product to product. But your basic accuracy for Magmeters is going to be anywhere from 0.2% of flow rate to maybe 0.5% of flow rate, depending again on the manufacturer and the product that you're putting into the pipeline. But this is the way to get that. Now, if you have a shutoff valve, either upstream or downstream, that 5 diameters up and 3 diameters down is still going to be good. If you start talking about a control valve where it could be partially open or partially closed, in most cases, we're going to recommend that that be expanded to about a 10 diameter of upstream and 5 diameter of downstream. What I'll also say is, and this I see this happen a lot, if you have a limited amount of straight run pipe, we recommend that you put as much upstream of straight run as you can make happen in your installation. It's upstream that creates the more consistent flow profile that the meter will want to see versus downstream. So if in doubt, and you have 6 diameters of upstream and 6 diameters of straight run to work from, I would say put as much of that upstream pipe, that straight run in the upstream as possible versus the downstream. So that's the basics of installation 101. Here's a couple of quick hints. If you are in a horizontal line and you have the ability to put even a diagonal, a slight incline to keep the pipe full before it goes to a partial pipe, that would be preferred. And if you've got a choice of mounting a flow meter at a high point in a line or a low point in a line when it's horizontal, always put it in the low point of the line, because that will give you the best chance of keeping the pipe full. All right, so what is the perfect profile? The perfect profile basically means, and this doesn't happen, so let's not worry. Let's this is ideal and it doesn't work. In a friction-free world, the perfect profile would have the same velocity at the pipe wall as it has in the center of the pipe. That does not happen because, again, in a world of friction, then basically what you wind up with is drag along the pipe wall a little bit and a slightly higher velocity at the center. Now, we take that into account as a flow meter manufacturer. So we are effectively saying that, and this is why I mentioned the calibration of the meter before, when we pick up a velocity of X amount of feet per second, that's a cross the pipe type of measurement based on based on what's going through it. And when we do calibration, we're basically doing a bucket stopwatch type of approach where we're batching flow through it, and we know exactly how much flow went through over a fixed period of time. And we can look at that and say, okay, the velocity profile is such. We know that the amount of process that went through at a given time was this, and as such, we can put in we can tweak a calibration factor that effectively takes into account that in a traditional flow profile, you're going to have some drag around the edges and better velocity in the center, and that's how we provide the performance. But when it leaves the factory, it's assuming these conditions. So if you don't have these conditions, which basically means if you don't have an ideal installation profile of the 5 up, 3 down, then that could change. And how it changes is what affects the ability of the meter to accurately respond. Now, what you will get is you'll get very repeatable flow. So if all you're worried about is repeatability, I'm not as nearly as concerned with the upstream and downstream. But if you are worried about your accuracy, and if that's critical, then your profile does matter. So that's just another view of a traditional profile. I'm not going to go into all of that, but I will tell you that here's what happens when you put elbows or T's, and whether they're and if you've got a double elbow, if you've got them out of plane. So what happens is not only do you get a change in the velocity profile within one axis, but you actually get you can actually get a profile change in a variety of the different axes. Anyway, whether it's a whether you're looking at the x-axis or the y-axis, and those flow profile changes can have an impact. It can be affected by the orientation of the electrodes, as compared to the flow profile. It can also be changed just by the flow profile itself. So what I'm basically getting at here is the more you've got with bends and T's and elbows and out of plane, that sort of thing, the more discombobulated your flow profile becomes, and the less accurate your meter will become as a result of that. So this is just to highlight those situations. Okay, so if we do have an imperfect pipe situation, what are some of the alternatives that are out there? Well, the first thing I'm going to do, and you may have seen this, you may have heard of it, you may already know about it, but recently a manufacturer, which will go nameless, responded to this particular situation by introducing the first, and to the best of my knowledge, only multi-path electrode magmeter on the market today. So effectively what they did, and you can see it in the meter here, they effectively have now 3 different channels or 3 different paths that they're monitoring using multiple electrodes. So instead of this traditional 2 electrodes, 1 on either side, you now have 6 electrodes, or 3 on either side. This is a very similar, if you're familiar with using ultrasonic flow meters at all. They're used in a variety of applications. A lot of times what an ultrasonic flow meter manufacturer will do, and we're no exception, is they'll recommend a multipath. And that, again, what that does is that gives you 2, 3, and in some cases 12 different paths that are monitored, and then the electronics does an averaging and puts all those together and gives you a flow that's reading that's maybe a little more in line with the velocity that should be seen versus the velocity that is being seen, because again, the multipaths are compensating for it. So they made that solution, and they went with 3 pairs of electrodes. Now, there's some things you've got to just take into account when you go into this type of a design. First of all, you're not going to get your optimum accuracy of, in this case, 0.2%. So the same manufacturer offers either a 0.5% or a 0.2% accuracy with straight run pipings per recommendation. And then they also offer a 0.5% accuracy without the inlet and outlet run. So in other words, with an elbow immediately in front of the meter body, or an elbow immediately on the back end of it, or both. There's a couple of things that you've got to take in mind, again, when you look at this. If you've got more electrodes, it basically means you have more opportunities for electro failure. So there could be everything from corrosion to buildup. These are typical things that can happen to a mag meter. And another possibility is if you do have too much corrosion or a process that attacks the electrodes and it either wears down or eats away the electrodes, that opens up a potential for for the process to get behind the electrode and behind the liner, and that can A, destroy the meter, and B, certainly make it make it less accurate, create bubbles in the background, etc. So the more electrodes you introduce into the pipe wall, the more opportunity there is for that sort of thing. Honestly, I think what's more important on that than that, from most of our customers' perspective, is that a 6 electrode design is a noticeably more expensive product, both to produce and also as far as the basic sell prices that you're going to find if you compare it to a traditional 2 electrode type design. So there is a premium associated with that. In addition, what you want to ask yourself is, does this price premium worth the improved performance? But again, in addition to the additional electrodes, the manufacturer actually also has an optional charge. So in other words, if you buy this 6 electrode meter, you're going to get the assumed accuracy with the inlet and outlet runs per the recommended installation. If you want without the inlet and outlet runs, with the special consideration, there's actually an optional code that adds additional costs, so it makes it even more expensive. And if you decide later on that you need that, to the best of my knowledge, you're out of luck. Either you've got to send the unit back to be recalibrated, but there is a fee that's associated with the fact that that you want a meter that to be installed in less than optimal conditions. And all of that is to basically improve your performance from around 0.2%, I'm sorry, to take your performance and make it up 0.5% as compared to an optimal accuracy of about 0.2. So that's one solution. The question becomes, is that what you want in order to achieve better performance? Are you willing to pay the additional price and the potential for additional failure points in order to get the 0.5% accuracy with a less than ideal piping consideration? So what can be done with the traditional 2 measuring electrode design? And that's what I want to talk about now. Now, really quickly, just so you know, you've seen and you saw it on the previous one as well. There are in many cases there are electrodes as well that are 90 degrees out of sync with the measuring electrodes, and those are grounding electrodes. That's a completely different beast. That's part of the grounding process required for mags, and I'm not going to get into that today. So technically, when we talk about a 2 electrode meter, there's actually 4. And when our competition talks about a 6 electrode meter, there's actually 8 points where there's electrodes because of the grounding that's included as well. So that being aside, just to touch quickly on what we've done and what we can provide, we have with our Mag 5100W product, first of all, we have a design that's slightly coned. It's a concentric cone. It's got about a 7.5 degree taper at the inlet, and then another 7.5 degree taper expanding it back out at the outlet. We do that for a couple of reasons. First of all, that gives you increased linearity because it actually helps to correct flow profiles to a certain extent. By doing that, it helps to remove some of the turbulence that might be created by elbows and T's going in, and it helps to create a more linear flow meter. It also increases the velocity just a little bit, and that means that your performance at the low flow air end of the meter is a little bit improved because the velocity is a little bit increased, and that means you've got a slightly higher voltage to work with there. You don't really lose anything at the upper end. And the reason you don't lose things at the upper end is because in a real world situation, while a magmeter is good to 31 feet per second, maybe 10 meters per second maximum velocity, what you have to keep in mind is that you should never be operating at that range. At most, you should be operating probably in the 12 to 15 foot per second velocity range, or about at 50% of the total capacity of the meter. So we really don't lose anything at the high end because you're never really measuring with any consistency at the high end anyway. At the optimum range that you're operating at, you're going to be fine on the upper end, and you're going to get a little bit better performance at the low end because of this slight taper. The slight taper does create a little bit more pressure drop than a full bore meter would, but in reality, it's only equivalent to about 3 meters of straight pipe run, so it's very negligible. All right, so what we did was we went to a third party and we basically said, we would like to be able to get certification as to what the performance of our meter is in less than optimal conditions. They then ran the meter through a variety of distortions using different methodologies that they had to simulate T's and elbows and other such stuff as that. They ran a lot of different tests on the meters, and at the end of the day, they came back and said, we can independently certify that the accuracy of your standard meter with in our case, our Mag 6000 electronics has got an accuracy of 0.8% or better. So we are effectively saying that with our standard meter, which is significantly lower in price, no special options, no special calibrations, that we can provide a 0.8% accuracy statement to our customers for the installations when the installations are less than optimal. Okay, so that's pretty much what I wanted to talk about today. So just a real quick, let's go over some of the key points. Magmeters are basically obstructionless designs. They have no moving parts and they measure conductive liquids. So that's Magmeter 101. For maximum performance, we recommend 5 diameters upstream, 3 diameters downstream from the center of the meter, and we want the pipe to remain full at all times. 5 diameters up, 3 diameters down is typical for basically every magmeter manufacturer that's out there as far as recommendations in order to achieve the optimal performance of the meter as specified in their catalog, technical data sheets, whatever you want to call it. When you talk about less than ideal conditions, manufacturers basically have taken 2 different approaches in order to maximize the performance. And that's what we talked about today. When you talk about, one would be to adding the additional electrodes. It does get you an accuracy of 0.5% in less than optimal conditions. There is a premium price adder, not only for the 6 electrode design itself, but also for the 0.5% accuracy in non-standard conditions. So you basically have to pay for both if you want to make sure you get you get the full benefit of the meter's ability to get 0.5% accuracy in less than optimal conditions. At the moment, the product's been around from our competition for a little over a year now. You have an increased delivery window versus a standard 2 electrode meter. And as I mentioned, the additional adder. And again, maybe not overly critical, but something just to keep in the back of your mind. Every time you add more electrodes being pushed into a liner, you provide more potential points where you could fail. A meter could fail if for some reason the process is able to get behind those electrodes, any of them, and in behind the liner. So the other option, the one that we've gone with, is going with outside testing and certification of our existing meter offering. So our standard meter, our standard 0.2% meter will offer 0.8% accuracy or better with less than optimal conditions, without any premium price or delivery impact. No need for any specials, designs, or configurations. So what does that also mean from our perspective? It basically means that if you're a customer that already has the product, the product we've been talking about today installed out in your process, we're saying right now that meter's good for 0.8%. You don't have to do anything with it, and we can provide a document to you that basically confirms that for you if you want to use it for your QA needs, etc. So that's you know, it's just it is what it is. It's our standard product, and we just had the testing done to effectively confirm what the performance would be in these circumstances. All right, so at this point, I'll go over to Jim, see if we have any questions, or we can just open up for questions, and you know, whatever time we have left, I'm willing to answer just about anything on Max.
Thanks, Jack. Yeah, so at this point, I haven't seen any questions come through in the question answer box on the screen here. So I'm going to, sometimes I hate to do this, but I'm going to unmute all. And if anyone has a question, please ask it. If not, then we'll just wait a brief period of time and we'll end the presentation. So I'm going to unmute everyone. We seem to have lost Jack's audio. So you can see Jack's contact information is up on the screen. So I apologize. If you have additional questions, feel free to send me an email at jimh@lesman.com, and I can certainly work with Jack and get those questions answered for you. So I apologize, we can't hear Jack at the moment, but you can see Jack's information as well as on the screen, and he says he's muted. For some reason, I cannot unmute Jack. So we're going to end the presentation with that. So again, I apologize. Give us an email or give us a call if you have additional questions. Thank you for your participation. Have a great day.